You know, there's something that bothers me every time someone says we're going to send people to Mars. And I don't mean it bothers me in a bad way. I mean it bothers me the way a good puzzle bothers you at 3 in the morning. You can't quite let it go, because getting there, okay, fine. We can talk about that. It's hard, but you can sort of picture it. You light a tremendous fire underneath a rocket, and you fall upward for a while, and then you coast for months. And eventually this little red dot gets bigger and bigger, and you land. All right, wonderful, congratulations. But now, how do you get back? Now here's where it gets interesting, and I mean really interesting. Because most people, when they think about this problem, they imagine it's sort of like getting back from, say, a camping trip. You drove out there, you drive back, same road, same car, more or less. But it is nothing like that. Let me explain something first, and then we'll come back to this. When a rocket sits on a launch pad on Earth, most of what you're looking at, I mean the vast overwhelming majority of the mass of that whole machine, is fuel. Not the spacecraft, not the astronauts, not the instruments. Fuel. Something like 90% of the weight of a rocket at launch is just propellant. Liquid oxygen, liquid hydrogen, kerosene, whatever you're burning, just fuel. The actual payload, the thing you care about, is almost a rounding error. Now think about that for a second. To get off Earth, we need this enormous mountain of fuel. And we burn almost all of it just escaping our own gravity. Earth pulls hard, you see. It's a fairly massive planet. And getting away from it costs an enormous amount of energy. All right. Now here's the thing. Mars is smaller. Its gravity is about 1/3 of ours. So you'd think, great, it's easier to get off Mars. And it is, in fact. The trouble is, where did your fuel come from? You had to bring it from Earth. You loaded it onto your rocket on the launch pad. You burned most of it getting to Mars in the first place. And now you need to land, and land gently, which costs more fuel. And then you need enough left over to get back off Mars, and then enough to slow yourself down when you get near Earth again. Because if you arrive home going too fast, you'll just bounce off the atmosphere like a stone skipping on a pond, or you'll burn up. Neither one is good. So the math here starts to get, well, it gets a bit brutal is what it gets. I remember working through one of these rocket equations once, a long time ago, just for fun, because I find that kind of thing genuinely fun. I mean, some people go to the movies, I do rocket math, and the numbers just kept multiplying on themselves in this way that felt almost cruel. The amount of fuel you need grows exponentially with the speed you need to reach. They call this the tyranny of the rocket equation. And it really does feel like a tyrant. Every time you add more fuel to carry more fuel, the whole thing gets heavier, which means you need even more fuel on top of that, and it just keeps spiraling. Now you might say, well, what if we make the fuel on Mars? And that is actually a fantastic idea. You can, in principle, take carbon dioxide from the Martian atmosphere and hydrogen, which you'd probably have to bring or extract from water ice, and you can combine them through a chemical process and make methane. Rocket fuel, right there on Mars. From dirt and air, more or less. Isn't that something? And I think that is something. I genuinely do. But here's where I have to be honest with you, because I find pretending things are simpler than they are to be a kind of rudeness to the person you're talking to. This process, making fuel on Mars, requires a factory, a chemical plant that you have to build on Mars before the people arrive. Because if the people arrive and the fuel plant isn't working, then they are not coming home. Period. And building a factory on another planet with robots controlled from Earth with a 20-minute communication delay each way, fixing problems you didn't anticipate in an environment that will try its absolute hardest to break every machine you've ever made, that is not a small engineering challenge. That is a civilization-level challenge. And you know what the honest answer is about whether we can definitely do that? Nobody knows for certain. Not yet. We think we can. We're pretty sure we can. But the distance between pretty sure and definitely is, in this case, measured in human lives. Now wait, I want to back up because I've been talking about the physics and the engineering, and I haven't told you the part that really gets me. Even if you solve all of this, even if the fuel plant works and the rocket works and you lift off Mars perfectly and you navigate the 8 or 9 months back through empty space, you come back to Earth as a different person. Physically different. Your heart has gotten lazy because it hasn't had to pump against full gravity. Your bones have thinned. The radiation out there with no magnetic field around you, no blanket of atmosphere, it has been pounding on your DNA the entire time. Your eyeballs have probably changed shape from the fluid pressure in your skull, which changes in low gravity in this strange way that we still don't fully understand and that, frankly, I find disturbing. The human body was built here. It was shaped by this planet over an enormous stretch of time, every cell calibrated for one gravity, one radiation level, one set of pressures. And you're asking it to survive somewhere that never once in 4 billion years was consulted during the design process. I can't tell you that's impossible to overcome, but I can tell you that we don't yet know how. That's the honest answer. We don't know. So here's where we stand. If I'm being straight with you, returning from Mars is not impossible the way flapping your arms and flying is impossible. It's not forbidden by physics. Nothing in any equation I know of says you cannot do it. But it requires solving more or less simultaneously the hardest rocket engineering problem in history, the hardest life support problem in history, the hardest remote manufacturing problem in history, and a medical problem we have never fully solved because we have never had anyone stay in deep space long enough to know what it really does to a person over time. And all of this has to work, not mostly work, not work well enough. All of it, because the margin for error out there is exactly 0. Now, does that mean we won't do it? I don't think so. I think we probably will. I think eventually some group of very determined, very brilliant, slightly crazy people will figure it out. And I find that completely, utterly astonishing, actually, that we could do this, that we're even seriously asking the question. But the next time someone tells you the hard part is getting there, well, now you know.